Assalamualaikum and hi to all my viewers. In this video, me and my teammate are going to talk about progress in liquid field detectors for radiation detection. Here are my group members. We have Aina Safia, Atrevena, and myself Aisha Hakim, Nubalkis Batrisha, and Putri Eliana Jiha. First, interaction. Liquid field detectors have become a vital technology in radiation detection, used in fields such as medical diagnostics, national security, and environmental monitoring. These detectors leverage the unique properties of liquids, such as high density and easy manipulators, to detect various types of radiation with high sensitivity and resolution. Recent advancements in material science, photo detection, and signal processing have significantly enhanced the performance of liquid field detectors. Improvements include better energy resolution, lower detection thresholds, and increased reliability, making these detectors suitable for more demanding applications.
Okay, now I'm gonna explain the scientific, instrumental, and application of our topic. Okay, so firstly, I'm gonna talk about the liquid xenon detector for medical imaging. Example, positron emission tomography, also known as a PET scanner. So in the early 1970s, the possibility of application of liquid xenon detector in medical imaging was recognized. Liquid xenon is well known to be an excellent detector medium for gamma ray in the energy range from several tens of kiloelectrovolt to tens of megaelectrovolt due to its high atomic number and density. Also, fast scintillator and high scintillation likely comparable to that of a sodium iodide. So, for this reason, its use as a radiation detection medium has increased in recent years in numerous applications in particle physics, astrophysics, and medical imaging. So, the application that use the liquid xenon detector is application for positron emission tomography scanner. Okay, this technology is a medical and a research tool. It employed for the precise identification, staging, and monitoring treatment of a cancer as well as a brain imaging and diagnosing disorder of the central nervous system. In the work of Lauve, he pointed out the advantage of using liquid xenon for positron emission tomography. He suggests using a two virtue of liquid xenon scintillation and charge for fast timing and precise positioning, respectively. However, the problem of detection of small charge signals remains. How does a PET scanner actually work? So, in order to satisfy high counting rate requirement for a PET detector, the electron collection time need to be as short as possible. This leads to a multi-sectional concept of the chamber. If you can see, this picture represents schematically the design of the chamber. It is composed of an array of a cell of 1 cm width separated with a thin cathode plate with a plane of collecting wire in the middle and cells are 60 millimeter long and 50 millimeter high. For this geometry, the probability for a 511 kiloelectrovolt gamma ray to interact with liquid xenon is about 73%, and the maximum electron collection time is 2.2 microseconds. Okay, next, the wire 50 micrometer diameter spaced by 2.5 millimeter and connect in pair, each pair being re-individually with a low noise charge sensitive preamplifier. This approach to keep the drift field reasonably uniform without doubling the number of redout channels. To reduce the input capacitance, the preamplifier will install directly on the air side of the chamber, feed through and operate at the liquid xenon temperature. The low temperature version of Totem 2.2 hybrid preamplifier was used. The input noise measured at 100 degrees was about uh, 350 electron RMS. The scintillation is detected with a 2 PMT partially immersed into the liquid. Okay, that's all.
There's another instrument for the liquid field detector for the radiation detection, which is liquid scintillation counter. I will explain more about the environment protection in the nuclear waste management. So first thing first, what is liquid scintillation counter? It is an instrument and indeed a common laboratory technique to measure the radioactivity of low energy that release the alpha and beta particle. So what can the liquid scintillation counter do? This liquid field detector can make sure that the radioactive material will not spread to the environment. But how? This liquid detector, like liquid scintillation counter, can be used to detect the leak contamination. Liquid scintillator counter is mostly used to measure the level of the radioisotope. Liquid scintillation counter use the sample to combine with the scintillation cocktail that contain the organic compound to produce the photon that are released. So what is the scintillation cocktail? It is a solution that emit beta particle which can be detected by the liquid scintillation counter. Next, the photon that are released will be detected by the photomultiplier tube and convert into the electrical pulse and will be analyzed. The number of the intensity that are related to the level of the sample radioactivity. The radioactivity of the sample result from the photomultiplier tube will be analyzed is going to be compared to the radioactivity from the surrounding. So how can it be detect the contamination? The specific isotope will be focused to determine the presence to indicate the leak to prevent the further contamination. Other than that, liquid scintillation counter can measure the radioisotope that is contained in the liquid waste sample so that their radioactive waste can be characterized to decide to store or dispose the waste. The question is how? This is same as the leak detection, where the sample that is used to mix with the scintillation cocktail then emit a photon that is detected by the photomultiplier tube, then convert into the electrical pulse. However, the electrical pulse height will be analyzed to measure the height of the pulse and correlate it with the radiation energy. The pulse height creates the energy spectrum where the peak shows the different radioisotope release. LCS or the liquid scintillation counter evaluate the energy spectrum based on the energy spectrum of the radioisotope. Next is quenching correction. Quench is a decrease in system efficiency which caused by the energy loss in the liquid scintillation solution. But why does the quench correction is needed? To get an accurate energy that has been measured by lowering the energy spectrum of the radioisotope. Lastly, the particular radioisotope that are present in the sample by comparing the energy peaks to the non-standard can be detected by the liquid scintillation counter. The waste is categorized into three levels, which is low, intermediate, and high level waste based on the isotope that has been analyzed.
Next is the future development and innovation. The first point is enhancing detection efficiency. By maximizing the composition of liquid scintillator materials, researchers are aiming to enhance the effectiveness of detectors filled with these liquids. The goal is to improve the accuracy in measuring different types of radiation and their energies. This effort involves developing new formulations of scintillators that offer higher light yield and better energy resolution. These advancements are crucial for advancing capabilities in radiation detection and analysis, enabling more precise scientific measurements and application in fields such as nuclear physics, medical imaging, and environmental monitoring. Next is miniaturization and portability. Liquid field detectors are shrinking in size, making them highly practical for field use and portability. Recent advancements in electronics and detectors design have enabled the development of compact and sensitive sensors. These sensors are now capable of fitting into smaller devices without compromising their detection capabilities. This miniaturization trend is particularly beneficial across diverse applications. For instance, in nuclear security, smaller detectors allow for more efficient and discrete monitoring at checkpoints. They can also be deployed in medical facilities for precise diagnostic imaging or radiation therapy monitoring. Other than that, we have advanced data processing and analysis. Advances in machine learning and data processing methods are revolutionizing the field of radiation detection and identification, aiming to enhance both precision and speed in this critical task. Machine learning techniques are being applied to analyze large volumes of data collected by detectors, enabling more accurate identification of radiation sources and faster response times. In urgent situations such as security threats or environmental emergencies, the ability to process data in real time is crucial. Machine learning algorithms can rapidly analyze incoming data streams from detectors, swiftly identifying patterns or anomalies that indicate the presence of radiation sources. Last but not least is cost reduction. Ongoing research aims to lower the production costs of liquid field detectors while maintaining or improving their performance. By achieving cost reduction, these detectors could become more accessible and widely adopted across multiple sectors such as healthcare, industry, and research. Reducing production costs involves optimizing materials, manufacturing processes, and assembly techniques. Innovation in these areas not only aim to cut down initial investment, but also lower operational expenses associated with maintaining and deploying detectors.
In conclusion, the advancement in liquid field detector for radiation have significantly enhancing their sensitivity, imaging quality, compactness, and affordability. For example, these liquid field detectors are now more resistant to extreme environmental conditions such as very high or low temperature, enhancing their reliability and lifespan. These improvements make them invaluable in various fields, including medical imaging, scientific research, and security, demonstrating the ongoing evolution and expanding potential of this technology in effectively detecting and analyzing radiation.